Welcome to AI Paper Podcasts. Today we're looking at GOPT, Scaling Physics Simulation via Lifted Geometric Pre-training by researchers from MIT CSAIL and Tsinghua University.
And we are getting straight into it because the problem they are solving is massive. Neural simulators are incredible for replacing slow numerical physics solvers, but scaling them is completely bottlenecked by data.
Right, because generating a single high-fidelity training sample can cost 61,000 CPU hours. And you can't just pre-train on 3D shapes because static geometry has no notion of physics or dynamics.
Exactly. So GOPT introduces listed geometric pre-training. Instead of expensive physics solvers, they take off-the-shelf 3D shapes, shoot virtual particles at them with random synthetic velocities, and track where they hit the boundaries. This forces the neural network to learn geometry dynamics coupling without a single physics label.
The results are staggering. They built a 5 terabyte dataset of over 1 million samples in just 3 days using standard CPUs. Fine-tuning this pre-trained model on real tasks reduces labeled data requirements by 20 to 60%, doubles convergence speed, and works across aerodynamics, hydrodynamics, car crashes, and even light transport.
It's a complete paradigm shift for the field.
That's the TLDR. Okay, let's unpack this and see how they actually pulled it off. Because if you are an AI researcher or an ML engineer trying to build better foundation models for physics, you intimately know this pain.
Oh, absolutely. The data bottleneck.
Yeah, the data bottleneck. We haven't had our GPT moment in physics simulation yet, right? We have the compute, but we are starved for data.
Right, and it's because the landscape is just fundamentally different from NLP or vision. I mean, in NLP, you just scrape the web, you have web scale, self-supervised data, you mask a word, predict the next one, and you're good. The data is practically infinite. But in physics, every single label requires a full numerical solve.
Which is brutally expensive.
It really is. Take the Drive AirML dataset they cite in the paper. It's a benchmark for car aerodynamics. A single sample, one single high-fidelity fluid dynamics solve, takes 61,000 CPU hours.
61,000 hours. If you ran that on one core, that's what, 7 years?
Basically 7 years of nonstop compute for one data point. So, trying to scale that to 1 million samples is financially and mathematically impossible for most labs.
Right. So the intuitive workaround, and I think we've seen a lot of people try this, is to just say, well, we have massive repositories of 3D shapes already, like ShapeNet or Observerse.
Yeah, millions of free 3D meshes.
Exactly. So why not just pre-train the model on those, teach it the geometry first using like sign distance functions, and then fine-tune it on the physics later?
Well, the logic seems sound, but the authors point out a massive flaw here. They call it the geometry-physics gap. When you do native pre-training, where the model only predicts static features like sign distance functions, you actually cause negative transfer.
Negative transfer meaning it performs worse than if you just started from scratch.
Precisely. Because static geometry has absolutely no concept of movement. You're teaching the network about shape, but you're blinding it to flow and direction. What's fascinating here is how they visualize this in Figure 3 of the paper. They map out the spatial correlations the model learns.
Ah, right, the symmetric versus asymmetric issue.
Exactly. If you pre-train a model on a parked static car, it just sees the shape. So it groups regions symmetrically. It links the front bumper and the rear bumper into the same latent state because they're both just boundary structures at opposite ends. It learns perfect left-right and front-back symmetry.
But aerodynamics is definitely not front-back symmetric.
Not at all. Fluid flows from front to back. It hits the front, goes over the top, and creates this highly turbulent wake behind the car. It's inherently asymmetrical. So if you pre-train on static geometry, you are hard-coding the wrong spatial correlations for a moving system.
You're teaching the model terrible habits that it then has to unlearn during the fine-tuning phase. Here's where it gets really interesting, though, because they still want to use those free 3D shapes from ShapeNet, but they have to inject dynamics into them somehow without running an actual CFD simulation.
Right, because you can't run Navier-Stokes on 1 million random shapes. It would take forever.
So they use this concept called lifted geometric pre-training, and the math intuition here is just brilliant.
It really is. If you look at equations 3 and 4, they step back and say, look, physical systems are basically just particles moving under a velocity field. But instead of calculating the true, accurate physics velocity, they just make it up.
They just fake it.
Totally fake it. They take a query point and sample a random velocity vector, which they call v, uniformly from a bounded ball.
So they assign a totally random speed and direction to a virtual particle. And then what?
And then they just track it.
Hmm.
Because it's a random constant vector, the particle just travels in a perfect straight line. It keeps going until it hits the geometry boundary. They use an indicator function, 1 sub g, which just halts the particle the exact millisecond it hits the mesh.
And the neural network's only job during pre-training is to predict that specific feature trajectory over a fixed time horizon.
Exactly. Predict where the particle goes and where it stops.
Which is wild because, for you listening, think about what this forces the model to learn. By predicting these synthetic trajectories, the model is forced to understand that distant points in space are coupled together by flow, and it learns that physical boundaries interrupt that flow.
Right. It learns how a shape blocks movement.
Exactly. It moves the learning process out of native 3D space and into this higher dimensional lifted space that includes geometry and velocity.
And this solves the compute problem entirely. Generating these trajectories doesn't require a numerical solver.
Right, because tracking a straight line until it hits a polygon isn't physics, it's computer graphics.
Exactly. It's just ray triangle intersection. They use a highly optimized library called FCPW. Tracking 36,864 points takes 0.2 seconds on an 80-core CPU.
0.2 seconds.
Yeah. It is 10 million times faster than running a CFD simulation. 10 million.
That is just an absurd speed up. I mean,
Right, the aircraft benchmark is intense. It involves high Mach numbers like Mach 7, variations in angle of attack, side slip angles. It's highly compressible, complex flow. And GOPT still accelerated convergence by 1.3 times.
They also hit hydrodynamics with the DTC hull benchmark, predicting water flow speed and pressure on a ship's hull under yaw. Water behaves totally differently than Mach 7 air, but it still worked perfectly.
But the one that really stood out to me was the car crash benchmark, because this is solid mechanics.
Yeah, this one is fascinating.
It's predicting 2D von Mises stress during an impact. So the car crumples. It's nonlinear structural deformation. And what makes this crazy is that it's a surface-only simulation.
Right, you're not simulating the empty volume around the car anymore. You're simulating the stress traveling through the actual sheet metal. So how does the straight line particle pre-training even apply to that?
They handle it by configuring a decayed velocity field directly on the car surface.
So instead of shooting particles at the car, you are shooting particles along the surface of the car and simulating how they squash together in decay as the impact force ripples through the metal.
Exactly. And because the model had seen a million different shapes interacting with random velocities during pre-training, it already understood how vectors decay and accumulate against boundaries. It reduced data requirements for the car crash by 40%.
If we connect this to the bigger picture, we have to talk about the scaling laws in Figure 6, because this is the holy grail for foundation models.
Right. We know in NLP, if you add more layers to a transformer, it gets smarter. But in physics simulation, because the data sets are so tiny, you try to scale up a model like Transolver from 8 layers to 16 or 32 layers, it just memorizes the data. It overfits and performance crashes.
But GOPT fixes that.
It acts as an incredibly powerful regularizer. Because the model has already processed a million diverse geometry dynamics interactions, it doesn't overfit on the small fine-tuning data set. It allows the model to actually scale smoothly as you increase network depth.
Which is exactly what we need for a GPT moment.
Yeah.
But, playing devil's advocate here, how do we know it's the dynamics doing the heavy lifting?
Right, the ablation question. Is it the dynamics, or is it just because the model looked at a million 3D shapes?
Exactly. Maybe just seeing a lot of shapes is enough.
The authors tested that directly. They compared GOPT to Hunyuan 3D, which is a state-of-the-art SDF-based geometry representation model. It is the absolute best at understanding pure, static 3D shape.
And what happened?
Conditioning the physics model on Hunyuan 3D features barely helped at all. It didn't improve the physics simulation much over training from scratch. That proves definitively that having perfect static geometry is useless if the model doesn't understand motion. The dynamics lifting is the essential ingredient.
And you can actually see the model understanding those dynamics in Figure 7 with the dynamics-dependent correlations. Because it was trained on random velocities, you can basically prompt it during inference.
Yes, the prompting is so cool. If you feed the model a crosswind velocity vector, its internal attention weights physically shift to capture inclined diagonal correlation patterns across the car.
And if you give it a zero-speed vector, it just safely degenerates back to static geometry. It knows exactly how to respond to the direction of the flow.
The wildest proof of this universal prior, though, is the Radiosity benchmark.
Oh, the light transport one.
Yeah. They evaluated the model on calculating light transport, specifically shadows, in a Cornell box with a Stanford bunny inside.
which is governed by completely different physics equations. We're talking about photons and light bouncing, not fluid dynamics or metal crumpling.
Completely different physics. But despite that massive domain shift, GOPT captured the high-frequency shadow boundaries better than models trained from scratch. Because if you think about it, a light ray traveling until it hits a surface is mathematically very similar to the synthetic straight-line particles from the pre-training.
It proves the pre-training is truly universal across different physical regimes. So what does this all mean? For you listening, GeoPT provides a highly scalable, entirely solver-free pathway to build foundation models for physics simulation. It bridges the gap between abundant static 3D data and the expensive dynamics-coupled reality of actual physics.
And this raises an important question. If you look at the theoretical analysis in Appendix B, the authors point out that shooting these non-colliding particles at a mesh is mathematically equivalent to solving a continuous collisionless transport equation in phase space, specifically Liouville's equation.
Right. It's actually solving real math without knowing it.
Exactly. So here's a provocative thought for you to explore. If simply shooting random non-colliding particles at a mesh teaches a neural network the universal priors needed for everything from fluid dynamics to light transport.
What happens if we scale that up?
Exactly. What happens if we start pre-training with slightly more complex interactive synthetic physics? What if the particles bounce off each other? Could a fundamentally fake but computationally cheap physics engine be the ultimate bootstrap to unlocking artificial general intelligence's understanding of our real physical world?
That is a fascinating idea. We don't need to simulate the real world perfectly. We just need to simulate the fundamental rules of movement at a massive scale.
It could change everything.
It really could. Well, that wraps up our deep dive into the source material today. Thank you for joining us on AI Paper Podcasts. Stay curious and keep building.